Hello everyone, myself Cyrus Raj. Currently I am a third year BTech student in Bennett University. My enrollment number is E20CSE236. So today I am going to present you about my topic data races. So let's start. So, what is data race? So, data race is a condition or race hazard in electronics, software, or other systems where the system's substantive behavior is dependent on the sequence or timing of other uncontrolled events. It becomes a bug when one or more of the possible behaviors is undesirable. The term race condition was already in use by 1954. For example, in David A. Hoffman's, a German scientist, doctoral thesis, race condition can occur especially in circuits, multi-threaded or distributed software programs. So coming to the next slide, high-level data races. A program may contain a potential for concurrency errors, even when it is free of low-level data races and deadlocks. Low-level data races concern unprotected access to shared files. The notion of high-level data races refers to subsequences in a program where each access to shared data is proctored by a lock, but the program still behaves incorrectly because operations that should be carried out automatically can be interleaved with conflicting operations. As a realistic example of a high-level data race condition, we shall illustrate a problem that was detected in NASA's Remote Agent Spacecraft Controller. The problem was originally detected using model checking. The error was very subtle and was originally regarded hard to find without any actually exploring all execution traces as done by a model checker. As it turns out, it is an example of high-level data race and can therefore be detected with the low complexity algorithm presented in this paper. The remote agent is an artificial intelligence based software system for generating and executing plans on board a spacecraft. A plan essentially specifies a set of tasks to be executed within certain time constraint. The plan execution is performed by the executive. A subcomputer of the executive is responsible for managing the execution of tasks, and once the tasks have been activated, the data structures needed for managing task executions are illustrated. Coming to the next slide. So here you can see examples of data race. So here we have defined a process in which there is two tasks, task 1 and task 2, and they are using the same shared resources. So let's understand it properly. So let us start with the simplest example of data race. In the following diagram that we have, I have shown you task 1 and task 2 write values to the shared resources, shared var1 and shared var2. The task later read the values of the shared resources through the functions. So let us begin with a simple situation that has no protection mechanism established in the operation. So this is the figure of, like I have shown, is the simultaneous access to shared resources by two tasks without specific protection. So we may ask what values of shared v1, var1 does the function do as with shared resources 1. You may expect the value to be 1 1 since this value was written in task 1 immediately before the function call. However, without any protection mechanism, the value read may be 21 or in some condition even a corrupt random values. Because of the concurrent execution of task 1 and task 2, the shared resources of shared var1 may be written in task 2 before being read again. So without imposing protection mechanism, any code we write in STH WTS shared resources 1 cannot rely on a particular sequence occurring, and therefore a particular value of shared var1. If our code relies on a particular value of shared var1, then the data race becomes a bug. Data race occur when shared resource is unpredictably accessed by multiple tasks. Data races may not be easy, as we know, to understand because the execution of instruction does not follow the sequence in which the instructions are also written. Also, the result can change in each test run and making a data race difficult to reproduce and fix it. So coming to the next slide. So data races in software. So a race condition can arise in software when a computer program has multiple code paths that are executing at the same time. So if the multiple code paths take a different amount of time than expected, then they can finish in a different order than expected, which can cause software bugs due to unanticipated behavior. A race can also occur between two programs, resulting in security issues. So critical race conditions cause invalid executions and software bugs. Critical race condition often happens when the process or threads depends on some shared state. Operation upon shared states are done in critical sections that must be mutually exclusive. So failure to obey this rule can corrupt the shared state. A data race is a type of race condition. Data races are important parts of various formal memory models. The memory model defined in the C11 and C++11 standards specify that a C or C++ program containing a data race has undefined behavior. A race condition can be difficult to reproduce and debug because the end result is non-deterministic and depend on the relative timing between interfering threads. Problems of this nature can therefore disappear when running in debug mode and adding extra logging or attaching a debugger. A bug that disappears like this during debugging attempts is often referred to as a Heisenberg, and it is the name of a very famous German scientist, Heisenberg. It is therefore better to avoid race conditions by careful software design. So coming to the next slide, data races in critical systems. Software flaws in life-critical systems can be disastrous. Race conditions were among the flaws in the Therac-25 radiation therapy machine, which also led to the death of at least three patients and injuries to several more. Another example is the energy management provided by GE Energy and used by Ohio-based First Energy Corp, which, among other power facilities. A race condition existed in the alarm subsystem when three sagging power lines were tripped simultaneously. The critical condition prevented alerts from being raised to the monitoring technicians, delaying their awareness of the problem. This software flaws actually led to North American blackout of 2003, and GE Energy later developed a software patch to correct the previously undiscovered error. So coming to the next slide. So data races in networking. In networking, consider a distributed chat network like IRC. When a user who starts a channel automatically acquires channel operator privileges. If two users on different servers on different ends of the same network try to start with the same named channel at the same time, each user's privileges to each user since neither server will yet have to receive the other's such signal that it has allocated to that channel. In this case, a race condition, the concept of shared resources covers the state of the network, which each server has freely changed as long as it signals the other servers on the network about the changes so that they can update their conception of the state. of the network. However, the latency across the networks make possible the kind of race condition described. In this case, heading of race conditions by imposing a form of control access over access to the shared resources, say appointing one server control who hold what privileges, would mean turning the distributed network into a centralized one. So a race condition can also exist when a computer program is written with non-blocking sockets, in which case the performance of the program can be dependent on the speed of the network line. So coming to the next topic, so data races in file system. It is a very important topic. So please hear it properly. So two or more programs may collide in their attempts to modify or access a full system, which can result in data corruption or privilege escalation. File locking provides a commonly used solution. A more cumbersome remedy involves organizing the system in such a way that one unique process, that is, running a daemon or the like, has exclusive access to the file, and all other processes that need to access the data in that file do so only via inter-process communication with that one process. This requires synchronization at the process level. A different form of race condition exists in systems where unrelated programs may affect each other by suddenly using up available resources, such as disk space, memory space, or processor cycles. Software not carefully designed to anticipate and handle this race condition may then become unpredictable. Such a risk may be overlooked for a long time in a system that seems very reliable, but eventually enough data may accumulate or enough other software may be added to critically destabilize many parts of a system. An example of this occurred with the near loss of Mars rover Spirit not long after landing. All this solution is for software to request and reserve all the resources it will need before beginning a task. So if this reboot fails, then the task is postponed, avoiding the many points where failure could have occurred. Although each of those points can be equipped with error handling, or the success of the entire task can be verified afterwards before continuing. So a more example approach is to simply verify that enough system resources are available before starting a task. However, this may not be adequate because in complex systems, the actions of other running programs can also be unpredictable. So moving to the next slide. So data races in computer security. So any software race conditions have associated computer security implications. A race condition allows an attacker with access to shared resource to cause other actors attacker with access to a shared resource to cause other actors that utilizes that resource to malfunction, resulting in effects including denial of services and privilege escalation. A specific kind of race condition also involves checking for a predicate, then acting on the predicate, while the state can change between the time of check and the time of use. When this kind of bug exists in security sensitive code, a security vulnerability called a time of check to time of use is also generated. So arrays conditions are also intentionally used to create hardware random generators and physically unclonable functions. PUFs can be created by designing circuit topologies with identical paths to node and relying on manufacturing variations to randomly determine which paths will complete first. By measuring each manufactured circuit's specific set of race condition outcomes, a profile can be allocated for each circuit and kept secret in order to later verify a security identity. So coming to the next slide. So it's over. I hope you are able to learn something new today. Thank you.